Welcome to today's deep dive. Our mission today is to basically decode the invisible digital architecture that you interact with every single day. And we are working with this really fascinating stack of source material, specifically bachelor's degree examination papers in library and information science on ICT fundamentals.
And I know right off the bat, that might sound like an incredibly niche academic focus. Like, why are we looking at library exams?
Yeah, people are probably thinking, I'm not trying to be a librarian.
Right. But these library science exams are essentially the ultimate foundation for modern digital literacy. I mean, think about it. A modern library manages, stores, and transmits the sum of human knowledge securely across these massive global networks.
It's not just stamping due dates in the back of paperbacks anymore.
No, not at all. If you understand the mechanisms powering that library environment, you fundamentally understand how our entire connected world works. It just, it strips away all the marketing jargon of big tech companies and looks at the raw plumbing of the internet.
Yeah, the actual pipes. So even if you aren't prepping for an exam, understanding these fundamentals is the ultimate shortcut to being tech literate. We're going to use this framework to pull back the curtain on how data actually moves. But before we can map out a massive network spanning the globe, we have to look at the individual brains powering it.
The physical computers themselves.
Exactly, the hardware.
And to do that, the sources point us back to the foundational concepts developed by John von Neumann.
Oh, right, the von Neumann architecture.
Yeah, and the crazy thing is, most of today's computers, from the basic desktop sitting at the circulation desk all the way to the massive servers in the basement, they still rely on this architecture.
Wait, really? We're still using the same basic blueprint?
We really are. He provided the original blueprint for separating a machine's central processing unit, the CPU, from its memory and its input-output mechanisms.
Okay, so breaking it into pieces.
Right, because before this, machines were often hardwired to just do one specific task. Separating these components meant a single machine could be general purpose. It could be guided by different software to do entirely different things.
Okay, that makes sense. And the physical city center where all of these separate components actually connect is the motherboard, right?
Yep, the motherboard is the main event. It acts as the central hub holding the CPU, the basic input-output system, or BIOS, and the memory. It basically provides the actual physical pathways for electricity to flow between all these parts.
And when we talk about memory on that motherboard, the sources make this really critical distinction about RAM, which is random access memory.
Oh yeah, this is a huge one to get right.
Yeah, because RAM is strictly short-term memory. It's volatile, meaning it only holds data while the computer is actively switched on and getting power.
Exactly. The processor needs a place to hold the data it's actively calculating right this very second without having to wait for the slow mechanical process of digging through the long-term storage.
Okay, let's unpack this with a visual for you listening. So RAM is like the tiny desk space where you are actively reading a book right now.
I love that analogy.
Right. You can reach the information super quickly, but you can only fit so much on the desk. The hard drive, on the other hand, is the massive filing cabinet down in the basement.
Yeah, you can store a ton more down there, but it takes significantly longer to actually walk down, retrieve a file, and bring it all the way back up to your desk.
Exactly. And sitting between that physical hardware and you, the human user, is the operating system. The sources highlight these things called GRUB, or boot systems.
Right, which function as the initial gatekeepers when a machine powers on.
Okay, how does that work in practice?
Well, a bootloader like GRUB allows a single physical computer to choose between multiple operating systems before it fully starts up. So imagine a library technician. They could reboot a machine and choose to load into a really secure Linux environment for, heavy database management.
Well, I see.
Yeah, or they could reboot that exact same machine into a standard Windows environment for general patron use, all using the exact same underlying processor and RAM.
That's incredibly efficient. But regardless of whether that machine is running Linux or Windows, the way it actually perceives the world is fundamentally different from how we do.
Oh, completely. It's alien.
Because humans experience an analog world, like sunlight, the sound of a voice, continuous radio and TV broadcasts. These are all analog signals. They are natural, continuous waveforms.
Right, sweeping curves of data.
But computers operate entirely in digital binary. They only process zeros and ones, nothing else.
And the mechanism there just relies on electrical states. A 1 is an electrical pulse, and a 0 is simply the absence of a pulse. On, off.
So why did we switch? Why abandon the rich, continuous analog waves for this super rigid binary system?
It was entirely driven by the need for perfect data replication. Think about it. Analog signals degrade over time and distance.
Like copying a VHS tape.
Exactly. Every time you copy an analog cassette tape or even photocopy a physical piece of paper, a small amount of environmental noise gets introduced. The copy gets just a little bit blurrier than the original.
But a digital signal, because it's just a strict 0 or 1, doesn't have that ambiguity.
Right. The machine receiving the signal simply asks, is there a pulse or is there no pulse?
There's no in between.
Exactly. Because of that strict threshold, a digital file can be copied 1 trillion times or beamed across an ocean and remain completely, flawlessly identical to the original.
Which is huge. I mean, for a library system tasked with preserving human knowledge, abandoning analog for digital binary was just a necessary evolution.
Absolutely. So once you have these individual machines flawlessly processing zeros and ones, the next challenge is getting them to actually communicate without creating total digital chaos.
Right. How do they talk without talking over each other?
Which brings us to data transmission and the distinct modes of digital conversation. The sources outline 3. The simplest mode is simplex, which is purely one-way communication.
Okay, like a megaphone.
Pretty much. A traditional television broadcast sending a signal to an antenna on your roof is a simplex transmission. It only goes one way.
Got it. And then the sources detail half duplex, and they explicitly compare it to a walkie-talkie.
That's the perfect example. Both endpoints can transmit and receive data, but crucially not at the exact same time.
Right, the channel only flows in one direction at any given moment. You have to press the button, send your data, say over, and wait for the channel to clear before the other person can reply.
Right. And then the most advanced standard is full duplex.
Right.
This allows simultaneous two-way communication. It functions just like a standard telephone call. The hardware can send and receive those zeros and ones concurrently without the signals smashing into each other.
Okay, so deciding on that transmission mode is step 1. Step 2 is determining the physical scale of the network those signals will travel across.
And these networks scale up really systematically. At the bottom, you have the PAN, the personal area network, that's just connecting devices close to a single person, like your wireless headphones to your phone.
Right, and stepping up from that gives you a LAN, a local area network, that connects the computers within a single building, like one specific library branch.
Exactly. Then a MAN, or metropolitan area network, connects multiple branches across an entire city. And finally, the big one, the WINE, the wide area network, connects systems across entire continents.
The internet, basically.
Yep. And the physical infrastructure supporting these networks obviously has to change as the scale increases.
Right, you can't just run a standard cable across the ocean.
Well, exactly. For small setups, say fewer than 10 computers in a back office where strict security isn't really necessary, the sources note you might just use a peer-to-peer network. Every computer simply shares resources directly with the others. No central server.
But as you scale up to a LAN or WAN, the physical cabling becomes a major factor.
It does. The cables are the actual physical highways for our zeros and ones. The sources mention coaxial cables, which feature a stiff copper wire core surrounded by a thick insulating material.
That insulation protects the electrical pulses from outside interference, right?
Right. But for the massive high-speed demands of a WAN, networks use optical fiber.
Oh, fiber optics. This is where it gets cool.
It's amazing. Instead of electrical pulses moving through copper, fiber optic cables transmit data using rapid pulses of light through tiny glass strands. It is blisteringly fast.
Okay, so beyond just the material of the cables, the network architects also have to decide on the topology,
Yeah.
which is the physical shape and layout of the connections.
Right. And the two main ones are mesh and star. A mesh topology is highly decentralized. Devices have many redundant interconnections. So if a construction crew accidentally digs up and cuts one cable, the data simply routes itself down another path.
It routes around the damage.
Yeah, exactly. But a star topology, conversely, connects every single computer back to one central hub or switch. All lines lead to the center.
See, this is where I have to push back. If mesh topologies have all these great built-in redundant connections so nothing breaks, why would a library ever build a star topology?
It's a great question.
I mean, in a pure star setup, if that single central hub loses power, every connected computer goes offline simultaneously. It seems like a massive vulnerability to engineer into a system on purpose.
Well, what's fascinating here is the tension between theoretical resilience and physical reality.
Okay, explain that.
A pure mesh network is incredibly resilient on paper. But consider the actual geometry required to build one in a building. To connect every single computer in a 100-terminal library directly to every other computer, you're talking about an astronomical amount of physical cabling.
Oh, wow. Yeah, the walls would just be stuffed with wires.
Exactly. The cost, the literal weight of the cables, the structural requirements, it just becomes physically impossible to manage.
So the star topology is just a practical
Yes,
compromise.
precisely.
Hmm.
By running just one single cable from each computer to a central network switch, you drastically reduce the physical clutter and the installation cost. You accept the vulnerability of that central hub because it's the only thing that makes managing the physical space of the building feasible.
And I guess network engineers manage that risk by making sure the central switch has backup power supplies and, enterprise-grade hardware.
Exactly. You protect the hub.
Okay, so with the physical copper and fiber cables laid out in these star or maybe hybrid topologies, the system needs a way to ensure a digital request actually finds its destination. Like if you search the catalog for a specific ebook, that request has to navigate through a maze of routers to hit the correct server.
And that requires a rigorous system of protocols and addressing. The internet historically relied on IPv4, which is an addressing protocol utilizing a 32-bit structure.
And this is a huge deal right now because we are currently navigating a massive global transition from that 32-bit IPv4 system over to IPv6, which is a 128-bit structure.
Right, and the shift was necessary for a very simple reason.
Mhm.
The world simply ran out of 32-bit addresses.
Which sounds crazy because a 32-bit address space provides roughly 4.3 billion unique IP addresses. In the early days of computers, 4.3 billion addresses must have seemed functionally infinite.
Oh, they thought they'd never run out. But the landscape of connectivity changed completely. Today, it's not just desktop computers requiring an address. It's smartphones, environmental sensors, smart fridges.
And in the context of library science, it's RFID tags embedded in physical books. Everything needs a location.
Right. So IPv6 provides an address pool of 340 undecillion unique addresses.
Wait, 340 undecillion? Is that even a real number?
It is. And to put that 128-bit math into perspective, 340 undecillion means we could assign a unique IP address to every single atom on the surface of the Earth. Every atom.
Every single atom. And we would still have a massive surplus of addresses left over.
That is absolutely mind-boggling. So every single piece of hardware gets a distinct location. And the devices directing traffic between those locations are the routers.
Yep. Routers sit at the borders between local networks and wide area networks, and they rely on very specific protocols to communicate.
The sources detail two really crucial routing protocols here.
Yeah.
The first is ICMP, the Internet Control Message Protocol. It functions basically as a diagnostic tool.
Right. Routers use ICMP to report abnormal events on the network. So if a pathway goes down or a server becomes unreachable, ICMP sends an error message back to the source. It basically acts as a digital flare gun. Help, this path is broken.
Exactly. And for moving the actual data, routers use BGP, the Border Gateway Protocol. BGP is responsible for actually routing information between entirely autonomous systems across the global internet.
And the mechanics of how that data physically moves have evolved a lot too. Early networks relied heavily on circuit switching, which is, think of an old telephone switchboard operator physically plugging a wire into a board to connect two callers.
Right, the classic movie scene.
Exactly. A dedicated physical circuit was locked in between two endpoints for the entire duration of the communication. Nothing else could use that pathway while they were talking.
But that method is highly inefficient for modern data. The sources note that in the mid-1990s, cell switching became prominent.
Okay, how is that different?
Well, instead of locking down an entire dedicated pathway, cell switching chops data into small, fixed-size cells. This was chosen as the basic transport mechanism for technologies like BISDN because chopping data into uniform cells allows a network to seamlessly interleave voice, video, and text data over the exact same connection.
Oh, so one massive file download can't just hog the entire line.
Exactly. It takes turns cell by cell.
That makes total sense. And this protocol-driven relay race is especially visible when you look at email delivery, which the sources touch on. When you type an email to a librarian and hit send, the message doesn't just magically fly directly to their screen.
Right, it's not point to point.
No. It uses a sending protocol SMTP to travel from your local outbox to a regional mail server. It's very similar to dropping a physical envelope in a neighborhood mailbox, which is then moved to a regional sorting facility.
And the message just waits on that server. It sits there until the librarian actually opens their email client.
Right, and at that point, their system uses a distinct receiving protocol like POP3 or IMAP to actively reach out verify the server, and pull the message down to their local machine.
So moving all this data flawlessly around the world is an incredible feat of engineering. But honestly, it doesn't matter if you can't actually find what you're looking for once it arrives.
Yeah, a giant pile of data is useless if it's not organized.
Exactly. The raw data needs structure. And that is where the library's real power lies, sorting the infinite.
Which brings us to database management systems, or DBMS. A DBMS is basically a collection of programs that allows a system to create, store, and modify massive amounts of data. And according to the sources, a modern DBMS operates using 3 levels of data abstraction.
Right, and the concept of data abstraction is really just about decoupling the underlying messy machinery from the user experience.
Okay, break down those 3 levels for us.
So the lowest level is the physical level. This describes how the raw zeros and ones are actually literally stored on the magnetic sectors of a hard drive. The highest level is the view level, which is the clean, formatted screen the librarian actually interacts with at the desk.
And the middle.
Sitting between them is the logical level, which maps the relationships between that raw data on the drive and the user interface on the screen.
And decoupling those 3 levels is absolutely crucial, right? Because it means a library can completely upgrade the physical server racks in the basement, changing the entire physical storage level without having to redesign the software interface the librarian uses upstairs.
Exactly. The logical level just acts as a translator between the new hardware and the old interface.
That's brilliant. And the architecture of the databases themselves has evolved too. Early systems often relied on what's called a flat file database.
Yeah, which is exactly what it sounds like. A flat file is essentially a single massive table, like one really long, simple spreadsheet.
Which sounds easy, but it's a nightmare to update. Like if a patron moves and changes their address, the system has to hunt down every single list that patron's name appears on and update the address manually.
It's so inefficient. That's why modern systems use relational databases. Instead of flat lists, the data points are linked. The database actually understands the relationship between the patron's ID, their address, and their checkout history.
So if you update the address in one place, the entire ecosystem updates instantly.
Exactly. The application can manipulate both transient and persistent data seamlessly across all these interconnected tables.
And to manage those relational systems, database administrators use specific languages. They use DDL, which is data definition language, to build the actual structure of the database, like defining the tables and the rules.
Building the house.
Yeah. And then they use DML, data manipulation language, to perform the day-to-day operations of inserting, updating, or retrieving the actual information within that structure, living in the house.
Great way to put it. And, retrieving information on the web requires markup languages to format the data for a screen. The sources offer a really great historical timeline here.
Yeah, they point out that the first significant markup language was SGML, designed by Goldfarb, Mosher, and Laurie. It basically set the standard for tagging text, so a machine could actually understand its structure.
And HTML, the language that builds literally all the modern web pages we use today, is actually just a specialized subset of that original SGML architecture.
It all builds on itself, and that foundation paved the way for the release of the very first web browser in 1991.
Right. Web browsers allowed users to navigate. But as the internet expanded, finding specific HTML pages required search engines. Traditional search engines crawl the web, indexing keywords and metadata. But the sources also highlight meta search engines, and they specifically cite Dogpile as an example.
Oh man, Dogpile, that's a blast from the past.
I know, right? But it perfectly illustrates the concept. A meta search engine doesn't build its own index. Instead, it acts as an aggregator. It takes your query, simultaneously submits it to multiple independent search engines like Google, Yahoo, and MSN, and then compiles all the combined results into a single list.
Which is super efficient. But to get precise results from any of these engines, you have to use search modifiers. You can use truncation, which concatenates words to find multiple variations of a root word, or fuzzy search, which gives you results based on approximations if a term is misspelled.
But the most powerful tool by far is Boolean logic, utilizing the operators AND or .full.
Yes, Boolean logic. This is my favorite part, because it's fundamentally about setting really rigid boundaries for a database query.
Right. How do you usually explain it?
It's basically exactly like ordering a pizza.
Okay, I like where this is going.
Right. So you tell the search engine, I want pepperoni A&D mushrooms, but not olives.
Right.
Boolean logic is just strict pizza ordering for search engines. By combining those logical operators, you aggressively filter out the noise, ensuring the database only returns the precise intersection of data you requested. Or, exactly the pizza you want.
That's perfect. And this shift toward complex databases and advanced search logic was necessary because of the evolution of the web itself.
Web 2.0, right?
Exactly.
Yeah.
Web 2.0 shifted the internet from a collection of static, flat file pages into highly relational, collaborative environments. Users weren't just reading text anymore. They were manipulating data, uploading rich media formats.
Right. The library catalog had to evolve to include formats like JPEG, which utilizes 24-bit color depth for high-quality images, and TIFF, which became the standard for image scanners and desktop publishing. The modern library is a fully interactive multimedia ecosystem.
Which brings us to the elephant in the room. It highlights a really critical vulnerability.
Ah, security.
Yeah, we've wired the fiber optic cables, implemented 128-bit IPv6, addressing organized complex relational databases containing vast amounts of user information. The final requirement is keeping bad actors out of that infrastructure.
Because protecting the system is arguably the most vital function of modern ICT architecture. The sources outline two distinct categories of security threats here. The first category includes viruses and worms.
Right, the automated threats.
Yeah. These are malicious software programs designed to attack the network infrastructure itself. They exploit vulnerabilities in the code to spread autonomously from machine to machine.
But the second category is phishing. And phishing doesn't attack the software, it attacks the human element.
Which is always the weakest link.
Always. Phishing is a deception explicitly designed to trick a user into voluntarily handing over valuable personal data like credit card numbers, email IDs, or passwords, usually by impersonating a trusted authority.
Click here to reset your bank password, that kind of thing.
Exactly. And to defend against both of these automated malware and human error library networks, implement the AAA security framework.
AAA, authentication, authorization, and accounting.
Right. It's a really rigorous protocol for controlling access to server resources. First, authentication. It verifies the identity of the user. Second, authorization. It determines exactly what files that specific user is actually permitted to access. And third, accounting. It keeps an immutable log of every single action they take while inside the system.
So to enforce that AAA framework at the perimeter, networks use firewalls and proxy servers. And I want to make sure we differentiate these. Because if a standard firewall functions like a heavy security door on a building, blocking unauthorized network traffic based on IP addresses, a proxy server is a much more sophisticated defense mechanism.
Yeah, a proxy server is brilliant. It acts as a dedicated computer system that performs crucial firewall functions directly at the application level.
Okay, so if the firewall is the security door, is a proxy server basically a security guard checking your ID at the specific door to the vault?
Better than that. It's like the security guard goes into the vault for you. When an external user requests a file from the library's database, they don't actually connect to the database. They connect to the proxy server.
Oh, interesting.
Yeah. The proxy server intercepts the request, examines it for malicious intent, and if it determines it's safe, the proxy server retrieves the file from the internal database and hands it back to the user.
Wow. So the external user never actually touches the internal database.
Never. The proxy server acts as an absolute middleman. And this separation is exactly how library protections ensure patron privacy. In systems utilizing modern distributed services and widespread RFID technology to track physical inventory, keeping external traffic physically isolated from internal data logs is just essential.
We have mapped out a phenomenal amount of invisible engineering today.
We really have.